Hi everyone, welcome back to another ZX Calculus seminar. Today we have Charles Chow who will be talking to us about how to grow sparse codes from a seed. So please, Charles, if you can start.
Yeah, thank you, John, for the introduction. And thank you, Sarah and John, for the invitation. So I'm very glad to be here to share with you guys about this recent work that Brad and I have done on growing sparse codes from a seed. Okay, so the archive number is over here. So our motivation is very different from I would say the conventional way of building quantum codes. Which sort of fuses together two classical codes, and you try to quantize the classical codes. But here we take more of a reductionist approach to quantum coding theory. So I'm myself a physicist, right? So I like to think about things in terms of atoms. So the atoms make up our complex world, and then you have the complex interaction with the atoms, and there are many really cool features that emerge from these complex systems. And you can ask whether we can do the same to the quantum codes, right? Whether they're atomic quantum codes such that once you fuse these atomic quantum codes, they provide you, they will help you construct more interesting and useful quantum codes that can be beneficial for quantum error correction. And the question is really, how do we get here, right? How do we get to these interesting, useful quantum codes from these atomic C codes? So we call it, or atomic Lego blocks, quantum Lego blocks, or all these names that I will use interchangeably. On the other hand, we can think about this really as an emergence problem, right? You have a bunch of really complex constituents. Each of the individual pieces are simple, but somehow there is something very non-trivial that emerges out of the complex interplays of these simple constituents. So the question we ultimately would like to ask is, what are the fundamental building blocks of quantum codes, and what are their limits and potential? And in this particular talk, the question we ask is, how do you grow a quantum LDPC code with generalization from these small atomic building blocks? So as the outline, I'll first give a brief primer on QEC, but I think most people here are already experts, and in fact, everyone here is an expert on ZX calculus. Nevertheless, let me give a quick introduction there, and then we're going to jump into a couple of examples, how we can build quantum LDPC codes from these simple C codes. We'll present some generic algorithms, which really is incredibly simple. You just turn your brain off, and then you just use the algorithm, and it gives you some codes with a guarantee. And finally, some sort of outlook into what we want to do in the future. Okay. And please also feel free to interrupt me at any time if you have a question. So as we all know, quantum codes are originally of interest for quantum error correction, right? We want to build a fault-tolerant quantum computer, and for that, we need quantum error correction. But they're also, important for many areas of physics, right? For example, in quantum many-body physics and quantum gravity. So it's not just a engineering problem. And to define a quantum code, right, the textbook definition is that I take some subspace in a physical Hilbert space, right? And the physical Hilbert space corresponds to the physical qubits that control in the lab. And then I want to be clever such that I take a subspace and I want to store my quantum information in the subspace such that it is robust against quantum errors and such as decoherence. So one such an example is the repetition codes on a classical computer, right? The repetition code is just that you copy the 0 a bunch of times, copy the 1 bunch of times. And the quantum version does just put cats around everything, and then that becomes a quantum code. And of course, it's a little bit more nuanced than that, right? So for a quantum repetition code, you can take arbitrary superpositions of these 000 and 111 code word, and then you can take the span of these two code words to form this subspace called the code subspace. And that completely defines, according to this definition, that defines the quantum code. Now we have a code. We also would like to check and correct for errors, right? So for the repetition code, this is fairly simple. So number one, we don't want to go in there and measure every single qubit, right? Instead, we measure the parity check operator. We just look at whether the two nearest bits have are the same, right? In this case. So you have one parity check operator that checks whether the first two qubits are the same, and you have another one that checks whether the second two qubits are the same. And if they're both the same value, then they return +1. So for example, you have a code word that lives in the code subspace, then this will give you +1 eigenvalues for both these syndrome measurements, or these are also called check operators. And then if you have an error that occurred in one of the bits, say for example the first bit, and then it's going to flip the first bit from 0 to a 1 and 1 to a 0. And that when you perform this parity check operation, you will return a -1 instead of a +1. And from these eigenvalues from the syndrome the syndrome measurements, you are able to tell whether error has occurred and where is the error. And by constructing the syndrome table, you can figure out where the error is, and then you can correct it. Okay, so that is the rough idea. And there's a more general set of codes called a stabilizer code, but it's really the same kind of principle, right? So you first construct the code subspace, and then you figure out how to check. You pick out a bunch of parity check operators, which correspond to the so-called stabilizer elements. And from these, by measuring these parity checks, you can figure out whether an error has happened or where it has happened, for example, and how you're going to correct it. So going back to the previous repetition code example, right, it is a stabilizer code. And it has a stabilizer subgroup, which is an abelian subgroup of the Pauli group that's simply generated by the two check operators that we had. And whatever states that are stabilized, that are +1 eigenstates of these operators, form the code subspace, which is what we saw from the previous slide. Okay. But on top of this stabilizer group, right? So these operators are parity check, and all the code words here that lives in the code subspace are +1 eigenstates of the check. You also have logical operators, which can, for example, change an encoded 0 to an encoded 1. So for instance, if you want to change an encoded 0 to a 1, you just put threefold tensor product of poly x's on all three qubits, all three physical qubits. So that will flip the encoded bit. And similarly, if you want to flip the phase of the encoded bit, you just put down the so-called logical Z operator. And then that will change the encoded 0 to encoded to 0, and then it will add a -1 phase for the encoded 1. So they act on the encoded information exactly the same way that you would expect, as if they're Pauli operators. Okay. Any questions so far? All right. So in this work, basically, all we're gonna do is to focus on these repetition codes, and we're gonna glue together these repetition codes in more. Let's skip this one. So far we've seen the following encoding process, right? So if you want to code, you want to encode a single qubit into 3 qubits in this example of a repetition code. And then you also have a way to represent the logical operations on these encoded qubits, right? So if where you will, for example, represent the logical X operator as the threefold tensor product of X, X, X. Okay. And the same for the logical Z and the logical identity. So now let's go straight into the diagrammatics, and let me just represent all these encoding processes with arrows as a diagram. And in this case, precisely a phase-free Z spider, where you let me take one of the legs as the input, and then the other 3 legs as output. So this diagram will represent for me an encoding map of the three qubit repetition code, where the input represents this logical qubit that I'm inputting, and then it scrambles it, and then it outputs a 3 qubit state on the output. Okay. Now, there is an operator way to think about this, right? In the literature, people call this operator flow or polyflow or polyweb and all sorts of names, but we're going to just treat it as an operator flow. So what this encoding process does to the operator is exactly represented by these things, right? And diagrammatically, you can visualize this also as a flow through a junction. So if you put in a x from the input leg, it's going to flow to three other x's out on the output, and that represents this particular representation of the logical x operator. And similarly, if you look at the logical z, right? If you put in a logical z on the input, what a logical z is could be represented as, a z coming out of any of the three other legs, or rather three other physical qubits, right? So for instance, this is one of the flows that represents this logical z operator. And finally, you could have identity flows, right? Where you have nothing coming in and then you could have something going out. So for example, if nothing, I would just put an identity here, and sometimes I literally just put nothing. And then you can still have flows that comes out. So for example, this will correspond to this operator here, right? Where the identity is represented as ZZ, a way to Z operator acting on two of the physical qubits. Okay. Everything good so far? Perfect. All right, so these are the junction rules and operator flows, and then I'm going to refer to it throughout the talk. And there is one additional piece that we will use, which is the X spider, right? Flip everything using a Hadamard. And then this now corresponds to a phase error correcting code, right? So you can similarly define a stabilizer group, but you flip all the X's to Z's and all the Z's to X's, and then similarly for the logicals. So yeah, so all the junction rules are identical to what we had before, except you change the letters and the colors, and everything stays the same. So Z flows to three Z's, one X flows to one X, and then nothing flows to two X's. Okay. So now equipped with these gadgets, we can build the quantum code, right? That corrects a single error. So the Shor's code is precisely represented as this diagram where you have first you encode your logical qubit into three physical qubits through a phase split code, and then you encode each of the three physical qubits in turn into three bit flip codes represented by these Z spiders. And this is called code concatenation, right? You just encode in the first layer of code, and then for each of the output of the first layer, you encode it into the second layer of codes. And this bottom layer catches the bit flip error, and the top layer code catches the phase errors, and together they can catch all the quantum errors. And from the operator pushing or the operator flow point of view, we can also deduce, right, what under this gluing of diagrams, how does the logical operator and how does the parity check of the new code can be generated? For instance, if I want to understand the parity check of this new code, I put down the parity check of one of these building blocks. So XX is one of the parity checks of this red code, the phase flip code. And then I can just flow this X to the boundary or to the dangling legs. And whenever it reaches a junction, I apply the junction rule, right? I remember that if you have a single X going in, the three X's come out, and then this flows to the six X's eventually on the dangling legs. And then that corresponds to a check operator of this short code, this 9-qubit code. Okay. And similarly, you can do the same thing with the logical operator, right? Where you put in a single logical X and you can flow it through this red junction to an output, which also is a single X. And then now you push it through one of the green junctions, and then that will come out three X's. And then that means a single logical X operator can be represented as a weight 3X operator on the physical legs. Okay. So one can repeat this exercise for arbitrary codes there, and then for arbitrary connections of these diagrams, right? And once you know the junction rules of all these individual nodes, then we can deduce the code properties, and we can actually do so efficiently using an algorithm. Okay, so any questions for this part? All right. Okay, so what is wrong? So it seems like we can get everything we want, right? And the code concatenation works very well. It allows to connect these very simple codes, the repetition codes, which individually do not correct any quantum errors. But when you connect them, right, now you can uh, build it into the famous shortcode, which does correct a single qubit error. And there are a lot of really good things about these concatenated codes where you can think of them as more or less the tree-like codes. Um, they're very simple, right? You have very good control over the code properties. For example, the code distance. And by the code distance, and the code distance really tells you how many errors you can correct in the code, right? So the larger the code distance, the more errors you can correct, and the better. Um, and it turns out that for concatenated codes, these are very simple to compute, and and for fault-tolerant gates, like especially transversal gates or non-proliferate gates, when we concatenate quantum codes that have these gates, it's also easy to generate these other elements. And there are already known efficient decodings, all sorts of tool sets that are available in fault-tolerant quantum computing for concatenated codes. So they're nice in a way, but they don't seem to be able to create all the interesting code out there. So for example, there are codes that have so n is the number of physical qubits, k is the number of logical qubits that you encode, and d is the distance. So it turns out there are codes that are really, really good, where both k and d are scaling linearly as n, as the number of physical qubits, as the number of physical qubits. So in some sense, they're sort of the optimal packing of my quantum information, and that they can also correct a lot of errors. And in particular, these codes can also be made LDPC. So I'm going to explain a little bit later on what that means. But practically, it means that I don't have to spend a lot of resources when checking errors, right? Because this is an error correcting code. I really don't I have to really keep checking errors and make sure there's no error happening. But for repetition codes, there's one major drawback is that every time you perform a check, you have to measure a very, really large operator. What I mean is the following, right? So if we call the shortcode, right, the parity checks will go through this operator flow, right? So previously on this first layer, you have a way2 check operator, but now it flows to way6. And if you want to keep increasing the distance of the code, you can imagine growing out this tree further using these red and green diagrams. But every time the x hits a green node, it's going to multiply by 3, right? So if you want your distance to be very large, by growing out several layers, the distance grows exponentially, but so are the checks, right? So the checks also grow exponentially with the number of layers. And that's not very good because when I do syndrome extraction, I have to measure all these operators, and that I have to introduce a lot of entanglement, and an error can happen during any of these steps. So this is really challenging, and you have to spend a lot of resources to deal with this. So instead, what you want to do is that you want to keep the checks as small as possible, so you don't have to waste so much resource when you're doing error correction. So coming back to this this question that we saw earlier was
I have a question.
namely, yes.
So earlier when you were talking about the errors or like the weight grows exponentially with the layers, but if you look at the connectivity that you showed earlier, you just have one layer, right? How would you have multiple layers in that diagram?
Good. Yeah. So what I was saying is that if you now grow out another thing, yeah. So here we only have 2 layers. Yeah. But imagine I grow the tree further by gluing some red nodes here and then agreeing some green nodes on the next layer and so on and so forth. So this will be my layer 1, layer 2, layer 3, layer 4. So when you increase the number of layers, right, the flow will also expand whenever it reaches a green node like this one. Right. So yeah, so every 2 layers it would multiply by 3. So that's the problem. Yeah. Does that answer your question?
And are you talking about like when you visualize co-concatenation in ZX diagram, that's what
Yeah.
you get, like this inner, like how this like layers of X spider, Z spider, X spider, and Z spiders.
That's right. Yeah, I was saying if you have a naive concatenation of the source code, then you will get this exponential expanding of the weights. Yeah.
Thank you.
Thank you. Good. Other questions? Erase this. Excellent. Thank you. Thank you for the question. So, yeah, so coming back to this, really, we want to ask the question is really how far can concatenation get? Can we get these codes that are good, where both on my k the and distance is scaling linearly with n, which we know is which we should know is possible, but we haven't really figured out how to do it with concatenation. And if you only concatenate repetition codes, right? If you only use these two ZX diagrams, what kind of code can you get? And this is what we're going to talk about for the rest of the talk. So first, let me talk about the LDPC codes. So these stand for low density parity check codes, where you can represent the code as a tensor graph, where each of these black node represents a qubit, and each of these boxes represents a parity check. So whenever a parity check checks one of these qubits, you draw an edge. Okay, so for the repetition code that we saw earlier, you have parity check on the first 2-qubit, parity check on the second 2-qubit. So the tensor graph looks like this. For LDPC codes, the degree of the tensor graph is bounded. So the repetition code is an example of the LDPC code. And it's been demonstrated a few years ago that you can, for these quantum LDPC codes, can actually have the number of encoded qubits and the distance grow linearly as n. But practically relevant codes, such as the surface codes, are also, they don't have as good a parameter, and nevertheless, they're also very useful for experiments. So let me just give you one quick example of the surface code, which is the LDPC. And here you will have the number of qubits which scales as L squared, with the length, roughly the length of each side. And you will encode one logical qubit, and the distance of the code is L, which is the length of one of the sides. And these red and blue boxes really just represent the parity checks, right? So whenever you have a blue box, here I just mean that you have a parity check that's x tensor x tensor x tensor x that act on these 4 qubits. And similarly, for a red check, is you have a z z z z acting on these qubits. And whenever you have a triangle, it means that I have z z a way 2 check on the boundary that checks these 2 qubits. And then if you have a blue triangle, it acts on these 2 qubits as XX operators. So all of its checks are bounded, have weights bounded by 4, and then you have weight 2 operators that are on the boundary. And it has logical operators, which are basically the strings that connect you the strings that that interpolates from one boundary to another. So if you have a logical X operator, and this is the operator that will flip the encoder 0 to encoder 1, right? And these will correspond to polystrings of XXXX that connects the top boundary to the bottom boundary. So it could take this shape, which is the shortest string, but you can also take a longer string, like that zigzags through the lattice and it goes down to the bottom. Okay. And similarly for the logical Z's, those are also strings, but they're also strings across, right? So they connect the left boundary to the right boundary. So you have multiple equivalent representations of this. So this could be one of them, where you have Z, 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 Z acting on this row, or you can have Z, Z, Z acting on some other row, or you can have some zigzag thing that goes through the lattice, as long as it connects one boundary to the other. And it is LDPC in that each check has at most weight 4, but each qubit is only checked by at most 4 checks, right? So this qubit over here is checked by at most of these 4. So that's the definition of LDPC code. So if you draw the tensor graph, this is what a tensor graph looks like on the right. So you can look at, you can see that all the degrees are bounded. Okay, so now let's ask, well, can we concatenate repetition codes to get this one, right? This is a standard code that everybody uses, like Google uses it, IBM uses it. So what about this conventional benchmark of the service code? And the idea is really simple. So in the previous shortcode example, we saw that when you concatenate the codes, we basically expand the operator flows, and then the expansion of the operator flows allows us to increase the code distance, right? So when you have a single X operator, it gets pushed to every single green node, it expands to 3X's, and that's how we increase the distance. But the problem is that I also increase the check weights, right? So now we just want something to decrease the check weight. And then there is a general principle that where we really want to contract the operator flow that is associated with the checks, but does not contract the operator flow associated with the distance. So let me explain how that could be done in an example. Right, this is what I just said previously. So now let's use this gadget a little differently. So previously we saw this X spider, and we used one leg as input and 3 legs as output. But now I'm going to change it up a little bit. I'm going to use 2 legs of this X spider as input and 2 as output. And then the operator flow on this junction will get organized a little differently, right? So previously, this is what the flow looks like. 1 Z goes to 3. But now if I change 2 of these to inputs, I have 2 Z's going in and 2 Z's coming out, if you orient it this way. But if you look at the X flows, if you have previously have 1 X going in, 1 X coming out, but now you can have 2 X coming in, but nothing comes out, right? So this will correspond to an annihilation of the operator flows. So if you somehow can orient this guy and glue it to a check where you have a bunch of X's coming out, bunch of X flows coming out of the checks, and then you glue this guy to 2 of the X's, this will annihilate the flows, right? And that would decrease the weights. On the other hand, you have this other thing, which is that if previously you have, if you have nothing coming in, you can have both coming out, but now you can in this reorganized thing, you have this corresponds to a 1 X flow coming in and 1 X flow coming out. So what you see is that if you have 2 flows coming in, it gets mapped to nothing. But if you have only 1 flow coming in, it gets mapped to itself. So there's something about this that you can use to decrease one object, but without changing the other. And that's the trick. So let me show this surface code example. So again, the X spider contracted with the Z spider, and now in this very simple repetition code, a concatenation, I constructed a 4-qubit code where first encode 1 logical qubit into 2, and then their outputs into 2 bit flip codes. And that creates this thing which has 4 physical qubits represented by these 4 legs, and it has 1 logical qubit represented by this 1 input leg, and it has distance 2. Okay, so but now let's say, well, and that's right. So the distance 2, the 2 just comes from the logical operator. So if you have logical Z, remember it goes across these 2. You have ZZ acting on these 2 qubits, and then if you have a logical X operator, it acts on X on these 2 on the column. So now let me increase the distance, right? Because increasing distance means that I can correct more errors. So one way to increase the distance is that let me just feed one of these wires coming out of the green guys into more red guys. Okay. Now each time I go through a red guy, it turns out that I will expand my flow for the Z operator. So if you previously had a Z going in here, you now have 2 Z's coming out. So that will increase. You can also visualize this as the following. Previously, you have a Z logical operator that's going across the rows. Now it gets stretched to a way for Z operator across this longer row. So the Z distance or the weight of the Z operator gets increased. And at the same time, you have to introduce these new checks that come with these repetition codes. Okay, so these are basically what's happening. Also on the diagrammatic side, you stretch the red triangles into red squares, and then you add these blue triangles along all the new edges that you add for the red squares. So this is the graphical transformation of concatenation. So now I increase the Z distance. I can also increase the X distance, right? So I want to now concatenate more of these green diagrams on the bottom layer. So each bottom node is gonna flow. It's gonna send a single x coming in to two x's coming out. So that's gonna expand the support of the x operator, and that will increase the x distance. Okay. So on the right diagram, what will happen is you will stretch these blue triangles into blue squares, right? So they will become way for x operator parity checks, and everything will look more or less okay except the middle one. So the middle one, because of this concatenation, the concatenation increases, expands the operator flow of the x, and then now increase this way 4x check into a weight 8x check with a bunch of other, way 2 guys that have to tag along because of the concatenation. Now this is problematic, right? Because I really don't want a way 8 thing. That looks really nasty. But I've increased the distance successfully, so the distance is now 4. Okay. So now I want to do something. I just want to get rid of this way 8 thing in the middle. I want to somehow reduce this way to way 4 things. And this is where our X spider with the 2 inputs will come in. So what it will look like was previously we had this 4-legged X spider thing, and we observed that if I choose 2 of its legs as inputs, it will map the XX operator to identity operator. So nothing will come out, right? So here what we imagine is that if I look at this way 8 check in the middle, where it corresponds to is some sort of flow of X operators throughout these diagrams. And eventually it came out as X, 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 X on these 8 legs over here. So let me draw these flows. And this is exactly what a flow would look like for this middle way 8. Now, I want to apply one of these guys and glue it to 2 of the outputs. So let me just do it here. So if I do that, right, there will be 2 X flows that are coming in, but then there will be no X flows going out. So that means I have done a weight reduction. And this is exactly what you will see. What is that you will reduce this guy into a weight 6 guy. But at the same time, this same diagram gives you another flow junction rule, which says that if there's nothing coming in, there could be 2 X's going out, right? So if you previously had the identity, previously you just had nothing, you erase all of these things. If they're all identities on these things, I can still have a flow that comes out of nowhere, and this XX way 2 thing will correspond to a new check that I've added to the system. So what I've effectively done is that every time, so in summary, what is happening with the red diagram is whenever you contract this red diagram with these 2 legs, it will split this large blue check into a smaller check of way 6 and a smaller check way 2. Okay. Okay, everything, maybe let me pause for questions. Yes.
Hi, can you somehow interpret this as like a generalization of a gauge code?
Yeah, you can.
Okay.
Yeah.
Okay, I see.
Yeah, very good. Yeah, so that's a great question. And also this diagram just corresponds to doing an XX measurement, right? So that's exactly like fixing a gauge. Great. Other questions?
I have a
All right. Yeah, sorry.
Oh, John, you first.
Yeah, so can I interpret this as like you're adding, sorry. You're adding like a weight 2 stabilizer, which overlaps with this weight 8 stabilizer. So then you can equivalently just view this weight 8 stabilizer as a weight 6 stabilizer.
In a sense, yes. Yeah.
And then also, I guess this thing anti-commutes with the weight 2 Z-type stabilizers that will probably change into a square because of that.
That's exactly.
Yeah.
I'm gonna get there right now. Yeah, that's a great question. Maybe, yeah.
Yeah. Okay, Sarah.
I think
Sarah?
so can I understand that the depth of your graph is the same as the distance of your concatenated code.
In this example, yes.
And when you add this junction, like this X spider, are you increasing the distance as well?
Good, that's a good question. So that's exactly also the next thing I'm going to talk about. Yeah.
Okay, thanks.
Okay. So good. So let me just talk about that. So it turns out, well, actually, this is the next thing. So the distance doesn't get changed at all because of the following, right? So remember that the X operator are just whatever operators that connect the top boundary to the bottom, so they act on the columns. So you can similarly draw two other X operators. You can draw an X logical here, and then there's going to be X logical here, right? Now, so if you let me just draw one of these, like one X operator here. But remember, this guy only maps if you have a single X coming in, it maps a single X out. So here, if you look at this operator flow, there's a single X coming out of this node, and it will go through this diagram to map to a single X. So it will map to, so total in overall, it will map a wave 4X operator to a wave 4X operator. So the distance of the X does not change. Okay. And now we can talk about the Z's. Now the Z's is the very interesting one in that, in terms of the Z, there is only this flow is allowed. You have two Z's coming in, two Z's coming out. Now, if you look at these checks, there is no single way to check that satisfies our flows because all of them will only supply a single Z going in. If you have this single Z, this check here, it will only have one Z on one side. So those things will get killed by this contraction. But instead, you have to look for a stabilizer that have both Z's coming out, and that corresponds to exactly the multiplication of these two way two Z operators. And if you multiply them, that becomes a square. And then the square is preserved. The square have two Z's coming in, and then you will get two Z's coming out. So in the end, on the diagram, it just corresponds to you merge two triangles into a square, exactly as John said earlier. And then you can check that this operation also doesn't change the Z distance. So it turns out that everything is preserved. The distances are preserved, but you just split the X checks. And coming back to one of the other earlier questions, this actually just corresponds to doing two body XX measurements, right? So whenever you do that, you do this, you have a split. Oops. Oh, yes.
Hi, so sorry. So this is a some sort of generalized Shor code, I guess. Is it well known in the literature that you do gauge fixing on a Shor code, you somehow get a surface code back?
Yeah.
So okay, so this is known in the literature.
Yeah,
and this is a pictorial representation via ZX.
That is right. That is correct.
Okay, thank you.
Yes. Yeah, I think the general term that we're looking for is the quantum compass code, and then you have different gauge fixing patterns in quantum compass code, and that will give you the surface code. Yeah.
Okay, thank you.
Thank you. Yeah. So this is a diagrammatic way of seeing that, and then that builds you the surface code. Now you can. So if you also do the same trick to the top two qubits over here, then you also can split this guy into a wave 4 thing and a wave 2 thing, and then eventually get the surface code. Okay, so and that is how you can do it. So you can keep doing this. We can concatenate and then rate reduce whenever it exceeds the weight limit, and then you concatenate, and then you increase the distance, but then you exceed the weight limit, and then you do this again. You use one of these green or red diagrams to reduce the weight. So you can keep doing this, and then you will grow out the surface codes to arbitrary distance. So this is how you could do it. So now we're going to generalize this lesson, right? So this operation by itself, even though I haven't seen it done directly in literature, it is not a far stretch from, say, the gauge fixing from quantum compass code. So now let's generalize this idea to the so-called subsystem codes. So one of the nagging things that it does in this example is that whenever I do this X weight reduction, it sort of merges two Z checks. And that is not very good because it can increase the check weight of the Z's. And if I just want to turn my brain off and create an algorithm, this kind of increase can sometimes be very problematic. So I want to do something that's slightly simpler. And it turns out to do that simpler thing, I need to go to these so-called sparse subsystem codes, where I will have X checks and Z checks that are still represented as this tetrograph, just like what we had before, except the X and Z's no longer have to commute with each other. So these checks will now form a non-abelian gauge group, and that is a generalization of the LDPC code. Nevertheless, we can apply a similar kind of procedure to this kind of code, where really what we do is that you start with a C code, like what we did with the surface code example, and the seed code has some sort of properties that, and then because it's a small code, you can always identify the a representation of the logical X operator and a representation of the logical Z operator. And now you can do the same trick. Let's concatenate to increase the distance. So the thing it turns out is the right thing to do is that for each, so the seed code could have contained multiple logical qubits, but for simplicity, let's just think of it as, there is one logical qubit. And then you find the logical Z representation of this qubit, find where the Z's are acting, and that's called the support of the logical Z operator. And then for each of the support, I'm going to glue it with a bit flip code, which is a Z spider, with one leg going in and two legs coming out. And that will increase the X distance. Okay. And now because I've expanded the X flow, that's also gonna, in general, ruin my sparsity limit. That's gonna increase the weight of the X checks. And now I'm gonna, what I do is that I simply pair up all the extra, I look at any of the checks that are overweight. And then I look at all the new qubits that I've added. And it turns out you can show that the new qubits that you've added by this concatenation step always form in pairs. And now you're going to apply a weight reduction gadget as given by this code, which is simply a 412 Bacon-Shor code, where you can think of it as 412 stabilizer code, right? So if you think of it as a 412 code, then this is a logical qubit, and then these four are physical qubits, and then you can glue, but instead of using the logical qubit as the input, I'm going to use two of the physical qubits as the input. And then this will act very much like the degree 4 Z spider that I've been using in the surface code example, where I just put two ins and two outs. And it turns out that this gadget would do exactly what we want and that would sparsify, that would rate reduce the X checks. And then there's a little bit of thing that I need to do with the Z checks by redefining where the checks are acting to just by doing stabilizer multiplication and to preserve the sparsity limit. And then you just repeat this. If you have multiple logical qubits, just repeat this procedure many times. And then this steps 1 through 4 will increase the X distance by at least 1. Okay, so that's what's going to happen. And finally, if you want to increase the Z distance, you just flip all the X and Z's and the red and greens in these steps, and then you just repeat these steps and everything works out. So really, to recap, you have a seed code initialized, and then you do these steps, you concatenate and then weight reduce. So that allows you to increase the distance while keeping the sparsity of the code. And finally, you do the same for the other type of the operator. And that you can, with that, you can basically grow out the sparse code. Okay. So let me just be slightly more.
Sorry, Charles, can I?
Yes.
You're saying it increased the distance by 1, but in your previous example, you were doubling the distance, right?
Yes. So this will be, you increase the distance by at least 1. Okay, so this will be a lower bound.
Okay.
Yeah.
And this is because you need to do these extra concatenations and they might decrease the distance again.
That's right. There are certain codes where you when you do the sparsification, it can decrease the distance back, but it doesn't quite decrease it back to where you started. It just decreases it back to where you started +1. Yeah.
Okay, cool. Thanks.
Cool. Let me see. I'm not sure how much time I'll have, so let me perhaps I can skip some of the details here. So basically, these are the flow rules of this 4-qubit thing, where I've suppressed the gauge qubit. So where I suppress the so-called gauge qubit, which we just leave dangling in the ZX diagram. And the flow rules here are just 2 in, 2 out. It's 2 in, nothing out, nothing in, 2 out. So this is very similar to what we had before for the x's. So all these 3 diagrams are very similar. But for the z's, now is different in that there are certain directions where you can have just 1 in, you have 1 z in and 1 z out. Okay, so that's in contrast with the X spider, where the only flow junction was that 2z in, 2z out, and that's what ended up merging the checks. So here's a diagram for what I just said of this algorithm in words, right? So suppose you have some code and it has some checks represented by these blue blobs. These are low weight checks, and then you identified some logical Z operator that is sort of supported on these physical qubits. Now, what you do is that you concatenate each of these qubits with the bit flip repetition code. So that will increase the X distance of the code, but at the same time, it also stretched out the checks by adding these qubits. And then it will also introduce some of these way to Z logical checks. But now for each check that I have increased its weight by, I noticed that it always increases in pairs. So this one increased by 2, this one also increased by 2. So I can apply this orange diagram or this combination of the red and green to reduce the weights of the x's. So after the application, I will have split the top check into a weight 2 check, a weight 3 check, and then a bottom as weight 2 check, and a weight 6. Okay, so this is what's happening, and it will convert these weight 2 z's into a so-called gauge operator in the gauge code. Okay, so here's an example more explicitly. So this is the so-called big and short code. So you start off with a seed. That's the 2 by 2. There are 4 qubits, and then these red edges are the Z checks, and the blue edges are the way to X checks. So they don't commute. Nevertheless, it's a code with distance 2. And then you just do the same thing we described before, right? You identify the support of one of the logical operators, and then you do a concatenation to increase the distance. And it turns out in this case that it increases the Z distance by 2, and that will also increase the Z check. But no worries, let me apply the sparsification on 2 of them, and that will split this weight 4 check into 2 weight 2 checks. And then you just do the same for the other one, and then you concatenate, sparsify, and you get back this. So the code that you get in the end is sparse. And it depends on what C code you started off with and how you grow it. You can get different geometries, get different dimensions. So this is a 3D big and short code. You can also get things that are weird, like this. So if you just forget about geometric locality and then you forget about, like, let me limit all my degree nodes to be some constant degree 4. Perhaps you have checks that are larger weight. Then you can grow out into some graph where you can show that all of the degrees in tenor graph are still bounded by exactly the number that you wanted. So everything is there. Okay. And let me just say that in this way, you grow out the code. There is a guarantee for the code properties in that the worst case asymptotic scaling of this algorithm will produce a code that's sparse, and then it has NKD where k times d squared is equal to n in up to some constant, or subleading stuff. So this is, if you know the BPT bound, this is exactly, it saturates the BPT bound, and it's not surprising. So it's saying, so what is it saying is that the worst code that you can get out of this algorithm is whatever saturates this bound. And this is actually the optimal bound because the code that we saw in the previous slide, this guy already saturates the bound, right? So this is so at this level of generality, this bound really is the optimal bound you can get. There's another result that's very familiar to the ZX folks, but not familiar to us until somebody pointed it out to us. In that now you can ask, so far, Charles, you've shown how you can grow these codes using repetition codes, great. And you gave us a distance guarantee, but the distance guarantee doesn't look very good. Yeah, you said the distance can maybe even grow linearly in certain LDPC codes. I don't see that. So are we limiting ourselves by using only repetition codes as code blocks? Well, actually, no. Right? So it turns out that all CSS codes can be built by gluing these 2-qubit bit flip and 2-qubit phase flip codes for the following reason, and that because it already showed this result that we found out later on. But as a physicist, I tend to think about this reason as, if you just want to prepare this code on a quantum computer and you consider some sort of measurement-based state preparation protocol, then you can always convert these preparation circuit into ZX diagrams. And when you have a CSS code, you can always show that the code can be converted into just the Z spiders and the X spiders all contracted. Okay, so all CSS code can be built using just the green and red diagrams, and therefore, and each green diagram represents the bit flip code, and each red diagram represents phase flip. So that's why everything can be constructed by these two basic elements. Yes.
Hi. So the primitives for all CSS code is basically these repetition codes. Is there an equivalent primitive for non-CSS codes?
Yeah, that's a great question. So I think if you want to get general stabilizer codes, you will also need to add a header bar and S, and that's it's unfortunately kind of a trivial statement almost because once you have those elements, you can generate all the Clifford processes.
I
Yeah.
see.
Yeah.
So even for non-CSS codes, the primitives are still 2-qubit bit flip and phase flip codes.
That's right. That's right.
Okay.
Yeah. Yeah.
Okay.
Up to local unitary deformations, then you're good. Yeah.
Okay. Thank you.
Thank you. But we see that there are actually more than CSS codes that these bit flip and phase flip codes can produce, right? Because we can also produce these subsystem codes. Okay. So in summary, and I'm also out of time, apologize, that we had a brief introduction to the stabilizer, to the QEC and diagrammatics, and then we shown some example, how do you build a surface code by growing these repetition codes, and we summarized our sort of distilled our conclusion from the surface code by constructing a more general iterative algorithm that allows you to build sparse subsystem codes that have this kind of scaling. And finally, all CSS codes can be built by these the simplest codes there is, namely the quantum repetition codes. As long as you're allowed to contract diagrams in this way where you have two or more as inputs and some other legs as outputs. Okay, so some future directions in that we want to keep growing sparse codes, right? We want to especially build codes that have interesting fault-tolerant gate sets. So here we only use the repetition codes, but more generally, we would like to use other Lego blocks that have different gate sets, preferably the ones that are difficult to build with the conventional coding theoretic approaches, like T-gate or CCZ gate or some other more exotic gates. So for those things, there is a work in progress where we show that a lot of this can actually just be generated from diagrammatics very easily. So we would like to combine these two ideas. Like one is to build codes with very interesting gates, and the other one is how do you build codes that are sparse and combine these, and you can try to build LDPC codes or other codes that have both interesting gates and sparse. Yeah. So that would be nice for practical quantum error correction. And the other thing is that oh yeah, so let me skip this thing. So this is how you can generalize it to build more exotic gates that are so-called addressable, non-Clifford. But you can also combine this idea with reinforcement learning. So this is something that we've done before, where you ask the machine to play with these Lego blocks, where each Lego block is a small code, and you just say, well, go play with the blocks and connect them in some ways, but then I want the code to have better properties. And I give it a candy if it produces a code that has better properties. And eventually it learns, oh, here's how I will perform, how I will grow the codes in order to maximize my reward, and then that will build the code that's very complicated. So by combining this rule that we have sort of now understood on the human side, you give it to the machine, you can teach machine to build sparse codes. And then there are a bunch of other things like computationally, you would like to characterize the codes that we just built. You would like to compare this method with other sparsification methods that are in literature. And the question on the coding theory side is, how do we improve this bound? Like, is there a way that I can find a better algorithm, a better way to synthesize sparse codes such that I get better distance guarantees? What are the other moves and combinations that are needed to get there, right? So that's an open question we'd like to explore in the future. Yeah, thank you very much.
All right, thank you very much, Charles. It's 4 o'clock. Do you have to leave, or do you have time to answer some questions from the audience?
I can stay here for a few more minutes. Yeah.
Okay. KH, if you want to start.
Hi. Sorry, I mean, I have two questions. So the first one is that is there sort of guarantees for like a fault-tolerant protocol? So I guess you're synthesizing codes at the moment, but are there guarantees? Let's say just say like circuit level noise. Is there a guarantee for protocols and beyond that? If I give you a qubit degree, like so LDPC, like how many checks does a qubit touches and how many qubits does a check touch? Can you synthesize a code that is sort of optimal in some metric, let's say? Yeah. Thank you.
Yeah, thanks. That's a great question. So at the moment, the answer is no, but I do not foresee any obstacle to extending this this idea to that regime, right? Because when I talk about fault tolerance, so here when I'm thinking about the growth of the cube of the diagram, I'm sort of implicitly thinking about, there's some sort of growth in space because I'm adding more qubits. But really, it doesn't have to be like that, right? So as you know from these, as you know well, in these ZX diagrams, I can sort of just think of it. It doesn't care about space or time, so I can bend some of these diagrams. As long as I use the right ones, I can bend them in sort of a time-like direction, and that will allow us, by tracking the right operator flows, I think that should be able to allow you to build some sort of locally fault-tolerant structure that, instead of having some distance that grow in space, you have actually some sort of distance preservation over time. Yeah, so that's the hope at least. Yeah.
Okay. Thank you.
Thank you.
Rosine and Leah?
Hello, thank you for the talk. Could I ask about how do you know when you concatenate with the non-isometric, for your example of the red spiders with 2 input and 2 output, since you're concatenating with something non-isometric, how do you guarantee the whole encoder is still in isometry? Is that guaranteed by the pairing algorithm, or does it necessitate having the gauge qubit?
Yeah, thank you. That's another great question. So that's guaranteed actually by you can check this by in a number of ways. So generally, indeed, it doesn't have to guarantee you an isometric map, but for stabilizers, you can always quotient out. So when you have a non-isometric map for stabilizers and these subsystem codes that I talked about, you can always just quotient out the kernel of this map, and then that will give you back to an isometry. So you don't really have to worry about it. For these, but diagrammatically, there's also sort of a way to see it. So what you want to do is that you identify your logical leg, in the diagram, you want to push the operator to, you want to push all these Pauli operators to the dangling physical edges. So if you can do that, then it's an isometry. Yeah, you can show that it's an isometry.
I see. So is there a guarantee that the pairing algorithm will always give you this property?
Well, so I mean, no. So generally, the pairing algorithm, well, if you just apply it arbitrarily, then it won't be an isometry. But then I say, but then it is really equivalent to an isometry up to a quotient. So you can always identify what quotient you need to take by doing this, yeah, by doing the binary parity check matrices.
I see. Thank you.
Yeah.
Thanks, Sarah.
Thank you for the talk. I wonder, so you start with the seed code that is a CSS like subsystem code, right?
Yeah.
And that code has a set of logical operations that are transversal. Is this correct?
Yes, we just care about the Pauli operators, so they're always transversal. Yeah.
Right. So when you grow the code and like when you do this what you call adjoining or conjoining,
Yeah.
how do you make sure that the fault tolerant operation that the seed code has would still remain fault tolerant in the sense of transversality after this growing up?
Yeah. Yeah, that is an excellent question. So let me first answer this for the codes that we have here. So for the codes that we have here is just that you always just have Pauli operators, and then whenever you conjoin stabilizer element, stabilizer atomic codes, you always get a stabilizer code, so you always preserve the transversality of Pauli's. But more generally, this is a great question, is that you don't want to just use these repetition codes. Perhaps you want to use some sort of quantum Riedmuller code that has a different kind of symmetry that has like transversal T's. And what you want to do then is that you want to identify these non-isometric, the equivalent of these X spiders that can contract, that can annihilate, say, some of the X flows or Z flows, but without changing the T's. Without changing the overall symmetry of the T. So what you have to do is that you have to pick Lego blocks that all have these transversal T gates. And then the quantum Lego formalism, then, which I didn't talk about, then guarantees that when you glue two Lego blocks together that both have transversal T's, there's a way to glue it such that all of them will have, the resulting diagram will also have transversal T. So the only modification is you want to identify these diagrams. You want to identify these atomic Legos that have the right symmetries, and then now you just want to glue together more general Legos.
So when you talk about the Lego blocks, you're talking about that Z spider where you have input and output. And like those are the things that you need to choose carefully.
Yeah, basically. So by general Lego block, I just mean any small quantum code that's convenient to you. So here's a quantum Riedmuller code that will have a transversal T, for example. So once you have these blocks, you glue them together, you get a transversal T code. And then there's also a way to generalize these sort of things so that they will look more or less like the non-isometric things, like the red thing, like the red spider, by choosing different legs as inputs and different legs as outputs. And that operation itself still preserves the symmetry, so you can still glue the codes that have transversal T. Yeah.
Oh, interesting. And another thing that I noticed is when you have that bigraph, you're saying, oh, like I want to attach my Lego block to a few of its legs. But for me, it seems like all of the legs are the same. Like if you look at the spiders from the same layer, is that you don't care like which one you're attaching to. You just care about the choice of the Lego blocks.
So I actually do care. So here there is a particular flow of the symmetries that I mean, if I probably don't want to act it on these two because they don't really do what I want. But I also don't want to act it directly on these. I don't want to act it vertically on. I don't want to act it over here because if I do that, that will split off these two qubits as a check, right? But then that will decrease my logical Z. Sorry, that will decrease my logical distance, a logical operator weight. So that's not good. So I do care which one I want to put. I want to orient my diagram very carefully. Yeah.
Then you have to check many times.
Yeah, you have to check many times, but that's what's the beautiful thing about this theorem or the algorithm is that it shows you that if you do this particular thing, then you don't have to check.
Oh,
Yeah, yeah,
thank you.
yeah. Thank you.
I also have a question.
Yep.
Sorry if you already talked about this, but your method allows you to really target the sparsity of the checks. Do you have any control over the locality of checks?
As in spatial locality?
Yeah.
I
I
mean,
guess you have some freedom in choosing where you do sort of the extra merges and stuff.
That's right. That's right. Yeah, and that so far we don't have a general theorem to do that yet. I mean, it's purely done in a case by case, fashion.
Yeah. Right. Thanks.
Thanks.
Any more questions in the audience?
So sorry, just like following up to John's question.
Yeah.
If you have an X error that originates in the input lake of the grand input lake, the one from the very top of the tree, a single flip will lead to a logical error, right?
Yeah. Yeah.
So the distance of the protocol that you've given is 1. So by that effect, it's not fault tolerant. The protocol is not fault tolerant, but the resulting code is fault tolerant. Well, the resulting code has a certain distance, right? Is that fair to say?
Yeah.
So the protocol. Well, the question I had just now is, can you construct a protocol that is fault tolerant on top of this this gluing procedure that you've described? Yeah. Thank you.
Yeah, thank you for the question. Yeah, so I need to let me be more clear about this. So this thing that we had here is not a protocol. I should not think of this as a fault-tolerant protocol. I just think of it as some sort of theoretical thing where I read it. If you actually have a protocol, what I really mean is that you probably want to repeat these X and Z spiders in some way over time where you don't change the overall number of qubits. And then you look at the local complexes formed by these, and I think it's very similar to what Yuchen and Arpit will talk about, or they have talked about, is that you want to form these loops or these local operator flows within these complexes such that the error does not propagate to somewhere else. Yeah, but this thing, if you use this as a protocol, it certainly is not fault tolerant. Yeah.
Okay, thank you.
Yeah, thank you.
Yeah, actually, I'm reminded by KH question. Like, so at the beginning, I understand your framework as a conceptual idea of like searching for new codes. But if you are growing the code from a subsystem code, could you actually rephrase this as a code switching protocol? Because code switching is also linked, like thinking about a subsystem code at the beginning, and then by gauge fixing, you're able to switch between different codes. Now, could you do this? Like think of procedure as a dictionary to tell us how to do code switch.
Yeah, absolutely, absolutely. So, well, I guess the thing is, I don't know whether how I would make it more useful. I mean, in this example, it is a code switching in the sense if I treat this short code sort of as an instant gauge fixed version of, like, say, the quantum compass code or some Bacon short code, then whenever you concatenate these X spiders, it is corresponding code switching because I'm sort of I'm measuring some gauge operator in some basis. So I would say yes, but we have not said anything. But I would say yeah. So I think that generally we should be able to say something, but we did not say anything useful in this paper. So that would be a great idea to think about this sometime in the future. Yeah.
Thank you.
Thank you.